Hello, everyone.
Hi,
Afternoon.
Professor.
Welcome to ITS 520. All right, so today on the agenda, we have several things. I'll give some time for questions on the homework assignment that is due tonight by 10 p.m. If you remember, you're working on the WECA lab. The Dropbox is located on the, if you go to the WECA module, you should see there WECA homework, the assignment, and it, so using WECA, analyze both the IRIS and MNIST data sets as discussed in class. The links to the data sets are located here, and the links are there, as you can see. All right, so that's the homework assignment, and you can submit, as I said, should by 10 p.m. Central Time. So that's one thing. The other thing is during the second half of lab today, Mitch Burke is going to walk us through how to get into Scholar. So if you remember, Scholar is the West Lafayette. Mitch, are you there?
Yeah, I am.
Okay, so that, you'll do that today, correct?
Yep.
Okay, great. So he will do that today. He's going to walk us through. So it seems like it's fairly simple, actually. You'll be able to, it's all web-based, which is really great. So I think all you need is a browser, and you'll be able to connect to the West Lafayette instances. So these are free for you to use during this semester as a student in 520. So this is a, what we have is a, students will have a GPU instance. So you'll have a Linux-based machine. You sort of remote desktop into it, and you'll be able to run on the terminal, your code basically. So anything that we do in the semester, and the great thing about it is, for instance, the pipeline might be that you run your code, you write your code, and you debug it with a small data set on your laptop. But then when you're ready, to run it with a big data set, you can just go ahead to the GPUs over there. And I believe they have P100s GPUs of NVIDIA. So if you don't know, that's like the most advanced, at least, one of the most advanced in any case. They're always creating new GPUs. But anyway, so it should be pretty good. I think with that, you'll have even more resources, your laptop, your VMs, and now the GPU, so you can actually do some big data projects. Because we will talk about that. One of the, when you go over a machine learning class, although we have to learn a lot of the basics and the principles, we have to address big data because that changes certain things, okay? So that's one of the things. So Mitch will walk us through that during the second half of the period today. Okay. I posted some materials about that on the Brightspace. So if you go to the resources tab or module, you'll see there's Scholar files for students new, and that should have everything. But don't worry about that. As I said, Mitch will walk us through that. All right, and then and that's it. So with that being said, let me share the Brightspace. You should be seeing Brightspace right now. So far, we've done the introduction. We've done WECA. WECA's, think of it as just one of many tools, right? One of many tools. You basically, hopefully, if you've gone through this WECA lab, you've gone through all the basic pipeline of machine learning. So now today we're going to spend a little bit of time on these two modules, performance metrics and data sets and features. So on the WECA lab, you had an opportunity to run several algorithms, to look at the metrics, and I gave you some intuition in the last class of how to determine if your algorithm, which algorithm was best. The accuracies I'm sure were probably pretty good. In both data sets, MNIST and IRIS are made, for academic purposes, one being a lot bigger than the other, none of which is big data though. So none of those is big data, even though one is 70,000 samples. That's just a data set, small data set really. All right, so you had an opportunity to use the performance metrics and to talk, go over data sets, features, and all of that. Today, now that you've had that practice, I'm going to go over some of the theory behind that, some of the intuition, and so we will discuss this to gain a better understanding. So I will do this week, and then next week we will begin the next phase of the course, which is dealing with manipulating the data through NumPy arrays. So that's a pretty important one. And then data scraping in Twitter, which is the idea that you're going to collect your own data. So now we will start coding, and these three we'll do some, remember Python is something that you should know a little bit about in this class. And you're not expected to know NumPy, so that's why I'm going to just give you a whole bunch of examples of how NumPy works. And I'll kind of start with that today a little bit when we start looking at data sets and features. But today is more of a theoretical set of lectures, just to give you more insight and intuition. And then next week, it's going to get more practical, concluding with your homework assignment, which will be gathering data from Twitter and data scraping some data. So you will have. Yes, somebody has a question?
Yeah, I was gonna ask about the homework, and so going through it, and I don't think I was the only one there, but I did not see the. I'm getting like a reverb going on. I did not see, like, for WECA, where you had that homework assignment where you had the list of what you wanted to see for like the 4 problems and things like, or like the using 4 different classifiers and things like that.
Yep.
I did not see that at first, so I started running it and I ran through about 7. But what did you actually mean by features? And so, like, were those like the test options that you were talking about, or just to have like 100% clarification there?
What was the question about features? Is that what it is?
So it says you will need to define what your features will be per data set.
Right.
As,
I mean,
and then
just
perform feature ranking.
yeah, just perform feature ranking. What I meant was identify the features are already given to you. So Iris has 4 features as we discussed, and then MNIST has 728 features, or is it 784? Because it's 20. Their images are 28 by 28. So you just take every pixel basically, and that's a feature. Yeah, 784 features. So that's really what I meant by that. I mean, the first lab is just really what I wanted you to do is grab. Are you guys looking at this?
Yeah, that's exactly what I'm looking at now. I just seen that actually like an hour or two ago.
Yeah, so we will use a program called Weka to perform data mining, right? And that's really what we're doing. We're just visualizing the data and getting some metrics. You will use, okay, so 2 data sets really to perform classification, which are Iris and MNIST, right? And I provided the links for those. I think I said that in class.
Yes,
I gave you the link,
I have
right?
those. I have those, and I think most of us have those. And I started analyzing them against, the different classifiers and things like that.
Yeah.
So I have done that, and then did the whole thing like, what is the percent that they were classified correctly?
Are you guys seeing the website right now?
Yeah.
Okay. So then the data sets are these, right? Fisher's iris, that's one data set. And then I provided train and test. You could have just taken train or test and used one or the other, or use both. It's really up to you how you do it. I didn't really specify anything at this time, but you could have. The reason why I put this is some of you have more powerful computers, so maybe train will, but test is smaller, so you could have just used test.
Okay, because I think last time you said use train, so I think that's what most of us ended up
It's
using.
fine. I mean, either one. It's really, if you think about it, as I explained with the percentage split, you take 100% of the samples, randomize them, and then do a split 70-30%. So it's really two data sets. You could have used this for train and then this for test. Or if you just do a percentage split or tenfold cross validation, which we will talk about today, you could have used either one.
So is the 80-20 split, is that considered like a feature, or what's the, or not? That's not a feature. So like, what do you
No,
mean
that's
by?
just a split. So let's go back to the document then.
Yeah, like what do you mean by ranking the features then of the 700 and some features?
So problems, you need to analyze each of the data sets using 4 different classifiers available in the Weka toolkit. And I think I showed you guys in the previous video at least 4. So that you should have. Then you will need to define what your features will be per data set. So if you remember in Weka, I showed you guys that you could go in and remove some features if you wanted to. So you didn't have to. I mean, all you have to say there is, I'm just going to use the features that are provided. And maybe identify that iris has 4 features, as we discussed in the class. And as I just said, MNIST has 784. Okay, because it's images of 28 by 28. So every pixel, basically every column and every row is a feature. And then it says here, you need to report classification performance metrics for each method and determine which classifier is better per data set. So that was really looking at the performance metrics like precision, recall, F measure, and all that. And then perform feature ranking, if you remember, that was one of the tabs. So you had to go to one of the tabs. And if you remember when I demoed this, you selected ranker, and then it would suggest a method. Then you would hit run, and then it would give you the features ranked. And so it would say like, this feature has a higher contribution to the model's performance. Does that make sense?
Yeah, that makes sense.
Got it?
Yeah, I think so. So basically, like, so say if we're doing the MNIST train,
Yes.
for where you put for number 2, what were your features per data set be? Or will you need to define it? So basically for that one, since the first one label is incorrectly defined as numeric and we have to change it to nominal, that would be something we put in there, right?
In number 2?
Yes.
You could say that, well, no, actually, so numeric to nominal has to do with the label only. So actually the features need to be numeric, and only the label is the one that sometimes it'll be numeric, but if you're going to do classification, you need to change it to that nominal. What I mean by define your features is, so here's the problem. So probably what you're confused about is that your understanding of the word features. So that's something that, out of 100 terms in machine learning, features is one of the top 5 that you need to really understand. So don't worry about it if you're a little bit confused right now. Over the course of the class, and very soon really, you will understand what that means. But in essence, features, the word features means how do we represent any data. So if I have a tree, I could represent it in a million ways, right? I can take a picture of it. I could put a microphone on it and then wait for the wind to blow the branches and then record that sound. Mm-hmm. Any way that you find to represent information about that problem, about the samples of that problem, is called a feature. So in the case of iris, it was, as we discussed, iris had, petal width, length, and then sepal width or something like that. So it was those 4 measurements about a tree of those 3 types of trees were the features, not the label. The label is, okay, for these 4 features, this is this type of tree. It's a sequoia or is a eucalyptus or whatever, right? And in the case of MNIST, we have images that are 28 by 28 in size, right? And so 28 by 28 is 784. So we just, imagine it's like a piece of cloth, you know, with 2 strings, one at the top, one at the bottom. You pull on it and you make that 2-dimensional into a 1-dimensional thing. It's called a vector. And every feature in it is basically now the pixels, each pixel. So like pixel at row 1, column 1, pixel at row 3, column 7, all, you know, all of them. And that's what the word features mean. So if you think of, you will need to define what your features will be per data set. To answer that question correctly, you would say, I used the 4 features of Iris, and I used the 784 features of MNIST. But you could have chosen, you know, I want to just use the cropped center 200 features of MNIST. So you didn't have to do that, but, you know, features can be whatever you want them to be.
Okay, I see what you're saying. So like by using filter, where you can filter them out and only run a certain amount of them or things like that, or
That's right.
certain type. Okay.
It's a filter. Just remember that all of this, MNIST is something that we will only use in the beginning, but we will move on to other approaches with sklearn and TensorFlow. But yes, exactly. That's why Weka is really good at that. As you start venturing into other things, you can always do a comparison. Okay, how did I do this in Weka? And the meaning of it stays in your head, although you're not using the tool so much anymore. Got it?
Got it.
Right,
Yeah.
Professor. I just have one question. Like, when I try to change the label from numeric to nominal,
Yeah.
all the rest of the data set is also getting changed. So
Yeah,
how
what
do I do
happened
it?
there is in the filter, you needed to specify. So when you select a filter, you get the name of it in a little white box, right? Just
Right.
next to the button. You needed to click on that white box, and then it opens a pop-up window. And in that window, it's going to say, which features do you want to do? And so really, let's say that labels, I'm assuming this happened on the MNIST data set. So it would have been like feature 785 or whatever. And so that's the one that you needed to select so that only that one gets applied the filter. Does that make sense?
Yeah, that answers my question. Thank you.
All right, great. Great. Any other questions? As I said, you know, the terminology, you know, I can see that the terminology is still not clear, and that's fine. Actually, today's slides go over more terminology. So that's good. Okay. So we'll go over more terminology today. Performance metrics, which it seems I had no questions about, is actually the one thing that is very important. It's actually a little bit difficult to grasp in the beginning, but I think I have an example that's pretty intuitive. And so, you know, hopefully that'll help. Okay. So are there any other questions about Weka? Okay, it seems like there's no questions. That's good. So remember, the homework is due tonight. All right, and then so it seems like we're ready to get started then. So I'm gonna start with, so if you go to the table of contents, if you go to the table of contents, you will see here, so I'm going to close Weka. You should be seeing this. So these 2 modules, right? So I'm going to start with performance metrics. I'm going to go over that one, and then data sets and features presentation. So hopefully a little bit more examples, a little bit more of the terminology that you definitely need to get down so that whenever I say something like features, samples, labels, you know, all this stuff, it'll just be, you know, immediately clear what I mean, okay? So think of these slides as understanding now that you have questions, which is good. All right, so let's get started then with, and before I forget, just for next week, make sure you've installed Anaconda in your environment, whether you're using Linux, Mac, or Windows, either one should work for these 3 labs. And so, or there's only, I think it's 2 labs, but no, it's actually 3, yeah. So these 3 modules, you know, just make sure you have Anaconda ready to go. All right, so I have the slides already open in my computer. So I think this will be very interesting and very, very informative. So I'm sure you'll like it. So let's see. I need to share. All right, so you should be seeing the slides right now titled Performance Metrics. Okay, so this is, you will always use this, okay? So you're gonna always use this for anything that you do. Most of the homework assignments you do in class, you will always have to report performance metrics of some kind. So there's a lot of performance metrics just in science, in data science, or in whatever you want to call it. But specifically for machine learning and for deep learning, what we're doing, we're going to see that there's a few standard sets of performance metrics. Now, there are more. There are certainly more versions, as you will see, I will hint at. But these are the general ones that you will always use. And you've already seen them, of course. And so now I'm just going to give you more of the intuition. So, you know, we'll talk about performance metrics. Okay, so that will be the main focus of this class. And then we will move into, you know, a little bit more detail about features. So what are performance metrics, right? So what are they? So we all understand a metric is basically, you know, like when you take an exam, right? So what did you get on the exam? Out of 100, did you get 90%, 80%? So intuitively, you know what that means, okay? So a formal definition of it is to determine how well a model performs on the data, right? So remember, it's always about this model, right? So we learned the last time we met that the data can be divided into at least 2 data sets, which are train and test set. And most of the time, that's what I will do. I will just divide it into train and test. However, there's also the validation. When you have, in particular, when you have a lot of parameters in your model, so let's say you have a lot of parameters that you need to tune. So this is called parameter tuning, because you try this set of this model, but if you tweak the parameters this way, it tends towards that way or some other direction. And so sometimes it helps to have a validation set. So what that means is that of all the data, you're going to split the data. Today, that's one of the things that we will talk about as well. How do we split the data? Okay, so usually I like to do an 80%, 20% split. That's just my preference. It's not necessarily better or worse, okay? But if you remember, the idea is that you always have a data set X and a column Y, right? And whenever you make sure they're aligned, and whenever you do the split, let's say 80%, 20, this becomes train, and this becomes test. So effectively, this, which was 2 things, right, X and Y, now becomes 4 things. X train y train, x test, y test. Now you can see how easily we could split this further and produce the other two, x validation, y validation. Okay, so that's also possible. But just remember, these are the splits. So whenever we're doing performance evaluation, we need to split our data because we need to train our model. So we need to train our model with this one, right? And then we test our model with this one. Now, the split is done before anything else, right? So that's one of the things that where you have to do the work. There's no magic for this, right? There's no button on Weka that does, you know, all of this, right? So you kind of have to, on your own, figure out certain things sometimes, so it takes a little bit of work. But we will see that later, especially as you start getting your own data, okay? So you have to do the training, you know, kind of build the pipeline yourself. And then once the model is trained, then you apply the test set. Okay, so, all right. So now let's move on to the next slide. All right, so far I've only introduced this idea. So how do you split the data, right? Splitting the data. There's actually at least two ways of doing it. And so far I have only discussed this one, you know, like 80%, 20% split. However, there's another technique called tenfold cross-validation. You probably saw this in Weka already. You probably saw it there. Maybe if you're curious, you actually said, huh, I wonder what happens here, right? I wonder what happens here. So the idea with tenfold cross-validation is pretty straightforward. Instead of grabbing the whole data set, so this is all and this is all, right? Instead of grabbing it and just doing an 80%, this looks more like 70-30. Instead of just doing a 70 and 30% split, which is random. I mean, what, at least in Weka, it's going to randomize the samples first, and then it's going to do the split. So that's good. You know, for statistics, you know, it's always good to kind of randomly select the data so that there isn't a pattern. And then cross-validation or tenfold cross-validation is this representation over here, where the idea is that you split this into 10 bins. So 4, 5, 6, 7, 8, 9, 10. So you can see I've split this now, instead of into 2 of 70 and 30, I've split this into 10 of equal size. So each one contains roughly about the same number of samples, right? They're all randomized, but now I have 10. So what cross-validation implies is simple. It's a simple idea. You're going to, instead of evaluating the model on the test set and the train set one time, you're now going to do it 10 times. Okay, so you're going to do it 10 times. And so what that means is that you're going to do 10 iterations. So on iteration 1, you're going to say, this one, I'm going to hold this bin out as the test set. And I'm going to use the remaining 9 bins as train. Okay, so that is the first iteration. And then you train the model, you evaluate it on that test set, and you record. So let's say, you know, iteration 1. And you record the metrics. You say that the F1 measure, I'm just picking one, is equal to 0.80, right? All right, on the test set. So great, you're done. Iteration 2, what do? In iteration 2, you're going to leave this one out, bin 2, and now you're going to use that and these, so these 9 bins, you're going to use them as train, and this one you leave out as test. So you can see now you always hold out one bin that the training phase does not look at to train the model. And then you see how it performs on that one. And then in iteration 2, you say, oh, okay, you know what? It went down. Interesting. All right, so there was something going on, right? There was something going on where this bin is a little bit more different than the other bins. And so that might create a problem. Then in iteration 3, you do the same. Right, so in iteration 3, now you leave this one out. That becomes test. And then train is these 2 and the others over here. Train. So now, once again, you train the model on these 9, right? And then you apply the model to this bin that you left out, right? And so that's gives you F1 measure of, once again, maybe it goes up to 87. So you can see, this bin is more similar to the rest, right? And you keep doing that. So I'm not going to do it for all, but you do it IN, and then, you know, you might have 0.5 for whatever reason on the last one, right? On the last one. So now you left this one for test, and then the other 9 for train. And so now, once again, you train the model on the 9, and then you apply the model to the test, the last one, this one, and then now you report the performance, and as I said, maybe the performance comes down to 0.5. And then once you do that, instead of, you know, maybe this model was giving you 81% F measure, it might turn out that this one, you're going to now take all 10, kind of take the average of them, and now this one comes out to 75%. Do you see this, guys? So there's 2 approaches here. There is the tenfold cross-validation, this one, which is this, or the 80-20% split, where you end up with 2 F measures. So now I ask you this question. If you're reporting your results to, you work in a company, or you're working on a project, and you want to say, okay, my model is really good, right? My model is really good because my F1 measure is, you know, which number do you feel you should report? Or which number do you feel would be the most accurate representation of the truth, of how well your model does given the data that you have? What would you answer? Can you guys hear me?
Yeah, we can hear you.
So what's your answer? Which number are you going to report, and why? You know, there's $1 million. Let's make it more interesting. It's a competition. Whoever gets the model with the best results wins $1 million. Which one do you report that you think is the most accurate or more correct? What would you say?
Would it be the tenfold?
So which number? Which number would you?
Two.
Huh?
Oh, the 75. Is that what you're asking?
Okay, 75. If you report 81%, you're gonna be the highest. You still want to stay with the 75?
Yeah.
Huh?
Yeah.
Okay. Why?
What didn't you say the tenfold? It goes through the process multiple times.
Uh-huh.
So therefore, it trains I mean, even though it does train like 9 different times, it trains like more than that versus the 70% of training, even though it has a smaller like testing size.
Okay. And why is it that, looking at the data multiple times, randomized, and, taking the test set from different parts, why is that better than just doing it once like this? I mean, it's randomized here, right? But why do you want to do the 75?
I think you have a less variation.
You have, yeah, it's more accurate, right? It's a more accurate representation of the world, right? You're making sure that by looking at it, it's like, when you're building something, right? You look at it from one angle, you look at it from another angle, you're just making sure that you didn't just get that one view of the thing, right? Or it's, you build a cabin and you say, oh, my cabin is great, but you really only lived in it in the summer. Are you sure that in the winter still warm enough? Make sense?
Yep.
So that's the intuition with this, is that by doing the tenfold cross-validation, you're making sure, right? Because it could turn out that, for instance, let's say that the data was annotated by 2 people, and it's just 2 people that are really different. One person really, it's about movies, and then one person really likes science fiction, and the other person really likes movies that are like romance, right? But as it turns out, when you collected the data, you basically, grouped it like that. This was science fiction, this was romance. And so if you're unlucky when you do the split, even if you randomize it, some of that pattern may stay in there. So the model may train mostly on science, but then in the test set, it'll get mostly romance. Whereas here, by breaking it up, you're kind of providing more variability on it. And so you're hopefully have a more accurate representation. Okay, so very good, Josh. So that was, even though this would be higher, when you say my F1 measure was higher at 81, but you told them that you only did 1 split versus the people that did a tenfold cross-validation, even though theirs was lower, people will trust this number more because they really think they want a model. Remember, whenever you do this, you cannot access the entire population for the problem, right? Out of the whole population, let's say that this is the entire population of the model, all the samples, you don't get all of them. You only get a sample of it, right? Sample of it. So tenfold cross-validation hopefully has an opportunity to look at more of it so that it generalizes better to the population, right? Which is really what you are trying to solve. Remember, you're trying to build models today so that you can apply them to problems in the future, right? To data that you have not seen before. And so that's why that, this kind of works better. All right, so certainly in Weka, you have this feature. We can simulate this, this feature also in code. We can just write it ourselves. sklearn has built-in functions for that, but it's straightforward really to do it ourselves. Okay? Are there any questions about cross-validation? All right, it seems that there's no questions, okay? So let's continue then with metrics. All right, so you had an opportunity in Weka again, kind of see the pipeline. You ran several algorithms, and you would get metrics like accuracy, precision, recall, F measure, the confusion matrix, and something called the ROC curve. Later on, we will see, as time permits, that there are other metrics as well for different problems. So for instance, for translation is the problem where you have a sentence in English and you build a model, and then the model gives you a sentence in Spanish, for instance, right? And so in this case, how do you evaluate the performance? So there are specific metrics for that. It's called the blue score, for instance. Okay, so that's one example of metrics that are specialized when we're annotating a data set. So if you're creating what is called a corpus, which is a data set, and the corpus is being annotated, let's say, by two people, so annotator 1 and annotator 2, you have to find a way to reconcile their annotation, because there's one thing that I want you to understand, right? So we talked about how machine learning is divided into 3 areas: supervised learning, unsupervised learning, and reinforcement learning, right? Those 3 ones. So in supervised learning in particular, we have a situation where we have a corpus that is annotated by 2 people. In supervised learning, what the machine learning algorithm is doing is it's learning basically what the human knows, okay? So if I look at sample, 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 and I have one annotator saying this is a cat, but then I have another annotator saying, no, 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 that's not a cat, that's a tiger. They're both right in that those are felines, right? But one sees a tiger for whatever reason. Maybe it's not really an accurate picture. It's more of an abstract picture. Imagine it could be like an abstract, like a Picasso, right? And it's an abstract painting. And in one painting, the abstract looks like, okay, this is a cat. Whereas for the other person, they look at it and, you know, that abstract to me looks like a tiger, I'm pretty sure. So really what's happening is each one of the annotators is putting in their perceptions of reality into the annotation, right? And so what's going to happen in machine learning is that the machine learning algorithm will learn that, okay? The algorithm learns, okay, that interpretation. And so don't forget that, right? That in supervised learning, the algorithm is really learning the correlation between the labels and the features, and that correlation is determined by the annotators, right? So sometimes then you're going to have a situation where the annotators are not agreeing, right? And that's called inter-annotator agreement. So there's metrics for that, okay? So there's going to be, some metrics for that as well, okay? But in particular, when we're just measuring the performance of our algorithms, we're going to look at these, all right? We're going to look at accuracy, precision, recall, F measure, and the confusion matrix. These, for now, these are the 1, 2, 3, 4, 5 different metrics or ways of measuring that we're going to use, okay? Are there any questions with this? No questions? All right. So performance classifier evaluation. So you've already seen this in Weka. As we start moving into Python and how we do things by scripting, we will be using a library called sklearn. All right, and within sklearn, other libraries like TensorFlow also have the same thing. TensorFlow usually has pretty much everything that is sklearn or NumPy. And so initially, though, our first new tool in machine learning that we will learn is just to use, to do the Python machine learning, we'll be using sklearn. So basically, we will use the sklearn metrics module for performance evaluation of our classifiers. Remember that for the beginning right now, we're mainly focusing on supervised learning, which means we have labels. We have labels. So I will show that this module can be used with sklearn classifiers and with TensorFlow classifiers, so we'll see that later. We will always do performance metrics, right? Every time we do anything in this class, we need to evaluate the performance of the model. Again, this will help to more easily understand deep learning and other things, because I will try for the most part to just use the sklearn metrics just to remove the complexity from TensorFlow itself. So when we start looking at TensorFlow, you guys will see, even though we'll take a top-down approach, I mean, it can be it's a little bit harder because there's a little bit more power than sklearn. All right, so here are the metrics, the previous metrics that we saw, but now in sklearn. Okay, so in sklearn, it's basically functions, recall score, F1 measure, score, precision, and confusion matrix. Usually what I like to do is I've already created a function, and we just, in every piece of code that we do, we just plug in that function. All you have to do is plug it in. It takes 2 arguments, and that's it. It'll give you the statistics. Okay, you can always change it however you want, but in general, you know, you can just have that function and always plug it in. So you really just have to understand this one time in the beginning, and then after that, you know, you should be good to go. What's important today is understand what the meaning is of all of these. And I'm pretty sure you already have a sense of what it is because you've taken a statistics class, and that's a very common thing to cover from the point of view of statistics. You know, these scores, they're actually the same idea. So today we're just gonna take a look at that. All right, so let's get started. Accuracy, that's the first one. You saw that in your homework with Weka. You used it, you analyzed it. It's probably the most intuitive score that we have, accuracy, right? Now, the best way to understand this is really to have a little table, which you can see I have the table here. Okay, so I'll explain, you know, accuracy basically has a meaning, but let's think of it in terms of this little table. So as you can see here, this just represents, let's imagine the test set. Okay, so this is just a test set. We are looking at it. We're basically doing a count, all right? So this is just a count of the samples in the test set. So we break this down into, let's say this is also a 2-class problem. So we have class 1 and class 0, right? So 2 classes. So what this implies is that obviously when you have something like this, you're going to have a certain number of the samples in the test set that are class 1 and a certain number of the samples in the test set that are class 0, okay? And so what this means here is these are the counts of the true 1 and the true 0. So this row here represents all the samples that are true class 0. And this row here represents all the samples that are true class 1. However, it's not just one cell, but 2, because it has to be broken up into what the model will do with that data. Remember that the model will take that data, you build a model, and now it's going to predict. It's going to be given each sample without a label, and it's going to say, oh, I think this is class 1. Oh, I think this sample is class 0. All right, and so that's what this table represents. It represents that out of the ones that are true, how many were predicted as true, that's A. Out of the ones that are true, how many were, even though they were 1, they were predicted as 0, which is incorrect, right? And the same goes for the next row. Out of all the ones that were true 0, how many were incorrectly predicted as 1? That's the letter C. And then out of all the ones that were true 0, how many did the model get right and classified as 0? That is D. Do you guys see that? And this little table, as you can see, we will use to define all the metrics, okay? All the metrics. So that we really just have to understand this really well. And then now it becomes pretty straightforward. So given this table, we can calculate accuracy, okay? And accuracy is gonna be out of all the A, B, C, and D, right, that we have there, out of all, which is that, how many were correctly classified? So that's only going to be A and D, because A is of the ones that were actually 1, A were predicted as 1, so they were correct. And of the ones that were actually 0, D were predicted to be 0, so they're correct. And so you only include those because, for instance, C and B, C is out of the ones that were supposed to be 0, C were classified actually as 1, which means that they were misclassified. Is that clear, guys? This is the most intuitive one, and it's something that we all understand really. You know, that's something that we experience in the real world quite a bit, and so we should have a basic intuition of this. Are there any questions about accuracy? All right, no questions, so it seems that it's clear concept. Now let's look at precision. Now these are a little bit different. All right, these will have a little bit more, these will have a little bit more, require us to think a little bit more, okay? So here, notice, precision is defined as A plus C, and then A divided by that, right? So that's precision. So it's the same idea as before, right? We have, now let's look, A and C, these. Right, so these are all the predicted ones, right? All the predicted ones. So basically what this implies is that out of all predicted, of the predicted as 1, this is, so the model said, you know, A and C, those are the samples there in those sets. A and C are the predicted, but out of those predicted, actually, only these, out of the predicted as 1, only A was actually 1. So of the predicted as 1 versus actually 1. So that's precision, right? So, you know, it's like saying, you know, I predict all of this, and here it is, boom. But really, out of all of that you gave me, only this was actually what I wanted, right? That's precision, okay? Any questions about that idea? No questions? Are you guys still there?
Still here.
All right. All right, so it seems like it's clear. I'll do an example in a second that hopefully will clarify it even further. Recall is the other one. Recall is now, let's analyze it over here. So recall is A plus B. So let's identify what A plus B is. Oh, here it is. A plus B. You see that? So, and then we have A. So what that means is A and B implies the true ones. The true ones, right? Of the true ones, A. How many are predicted as 1? So this is an important one because it's saying out of all the ones that I wanted this group of things, you know, but I wanted the real ones. And out of those real ones, how many, which are A and B, how many did I actually get? So it's, you know, like a Venn diagram, right? So that represents A and B, the true ones, but my model actually gets that, you see? So it actually only gets that little piece of the true ones, which basically implies that these are in error. Make sense? Yeah? All right, so then you have precision and recall, and these metrics, as you can see, they're giving you different information of what you want, okay? So this becomes more obvious when you're thinking about specific problems. So we will look at a couple of problems and why you sometimes, you actually, I should say, you almost never look at accuracy. Accuracy is there, but it's really the last metric in general that you look at. Instead, you always look at precision, recall, or what is called the F1 measure, which is a combination of precision and recall. Okay, so it's going to be a combination of the four. All right, so if there are no questions about recall, let's move on to the next slide. And you can see that here. F measure. F measure is, as you can see in the formula, precision and recall combined. Okay, it's defined as a harmonic average, and we will see what that means in a second. But basically, for now, just look at the equation. And I really just want you to understand the intuition that this F measure doesn't focus on precision, doesn't focus on recall. Instead, it focuses on both at the same time. So it's like saying that my model, when I measure F measure, the higher the F measure is, the more balanced are both the precision and the recall. So it's like you're saying, my model gets good recall and it gets good precision. And that's what I want. I really don't want a model that just does really well in precision, but really badly in recall. Just like I don't want a model that does really well in recall, but very badly in precision. Or a model that just does well in accuracy. No, no, no. I actually want a model that maximizes the precision, maximizes the recall, and that's really the optimal one. And so that's usually called the F measure. So whenever you do a report, describe a model to somebody, maybe write a paper, submit it to a conference somewhere, you're going to always define the F measure. That's really the metric that you often see there. Now, I should say, as a note, that I asked you to do algorithm 1, 2, 3 and compare them, right? So that means you looked at F measure for this, F measure for that, F measure for that, and you probably just picked the highest. I should say that there's a more complete way of doing this, and that is done with something called the t-test, or the t-statistic. All right, so the t-test we will cover later. That's if in WECA, you were using the Explorer, but if you had clicked on the button that says Experimenter, the Experimenter has the t-test feature, okay? You can also do this in Python. You can just write your own code. And so later on, we will come back to this. Interestingly, most machine learning papers do not include the t-test. They're mostly just experimental, whatever the results give you. But if somebody ever complained about, hey, you just showed the F measure, if you wanted to, and they say they want a more complete test or analysis, then that means you would probably have to measure each F measure using the t-test, which is, you probably already saw this in your statistics class, and it's really that definition in statistics, okay? So, but as I said, we will come back to that. I don't want to over confuse you, because I think that precision, recall, and F measure, just that relationship can be a little bit confusing in the beginning. So we will come back to that. But I want to make sure I mention it so that you're aware of that. Okay? Are there any questions so far? No? Okay.
I have a question, Professor.
Go ahead.
When we calculating F measures, and in order to do that, we have to calculate first precision, which is the previous formula,
Right.
and using a formula, yeah.
Yeah. So
Then
you
plug them
basically-
in,
look at the confusion matrix and you will grab the data from there and you follow the equations. So you have accuracy there, precision, recall, and then, I mean, you can just plug in
Okay, that's that.
things, right? I mean, it's the same
Yeah.
thing.
Okay,
But you always want to report all metrics, really. You know, as you saw in WECA. WECA actually gave you that little table. One was F measure, one was precision, one was recall. But what I'm saying is usually, like, let's say well, you're writing a paper, right? And in the paper, in the body of the paper, in the discussion, you have all of this. But in the abstract, you really only have room for, you know, a few sentences. So you don't have room for everything. So you want to say, okay, how can I best convey everything with one metric? F measure. Do you see
okay.
that?
Yep,
Does that make sense?
yes.
Okay, great. So that's the general intuition of that, okay? As I said, it's very important that you understand this because sometimes your problem will need to focus on one of these. Maybe precision is what you want, or recall. You know, it just depends. Maybe you can afford to miss things, or maybe you cannot afford to miss things. Do you see that? So in healthcare, for instance, you know, it's better to make an error but not miss something. Whereas if you're looking for just to become rich, right, you don't need to find all the things that make you the wealthiest person in the world. You just get some of them, right? And so it just depends. And so it depends on what your problem is. Okay. So let's continue. Okay, so now the confusion matrix, as you have seen, we will always use the confusion matrix. I am very big on this one. I believe it's very helpful. I think I sort of explained this a little bit the last time we met, but the confusion matrix is really a representation of, you know, how the model misclassifies. Where is it getting it wrong? So the intuition is really simple. You really want the diagonal to be the highest value, and then the off diagonals, you want them to be 0. So here we can see, for instance, that we have misclassifications there, right? So those are misclassifications. And so we want to figure out why there's a problem. So for instance, if I look at iris setosa, right? Out of all A, 49 were classified as A and 0 were misclassified. So that's really great. The model doesn't make a mistake. But it turns out that in B and C, apparently the features are getting confused because, or the model is getting confused by the features because out of 50 that were supposed to be versicolor B, only 46 were classified as that. And 4 were misclassified as C, which is virginica. Okay. Now, if we look at the next one, out of virginica, which is C, right? Out of 50 that were C for virginica, only 46 were correctly classified as C. That means that we had 4 misclassifications. So that is 4 that were supposed to be C were actually classified as B. And so there was an error there. Okay. And so that is, you know, a problem. Is that clear for everyone, guys? Are there any questions? Whenever you do machine learning for supervised learning, you will always have to do this analysis, okay? Very important. And keep in mind, we are using, I think, yeah, this is iris. And iris is, you know, very easy. I mean, it's a data set from Fisher's data set from late 1800s. I mean, it's very academic, but when we start looking at real data sets, you will see that, you know, it's just not, your data will be more, you know, numbers over here, you know, all over the place. You'll have more labels. I mean, it's just going to be more complex. So certainly there, the confusion matrix will provide you way more understanding of what's going on in your data. Okay? Any questions? Okay, no questions it seems, so let's go ahead. All right, round 2. I like to call this round 2. So this is, you know, like a battle. If the first round was tough, okay, so now hopefully this one will help out. So it's sometimes good to understand these things with an example. So let's take the example that you're a consultant, right? You're a consultant, you have your own firm that does AI, machine learning, data science, all that. And you've been hired by the Department of Homeland Security, and they want you to build a model, you know, to identify potential terrorists on flights, right? So, so let's get started. So, would you believe someone who claimed to create a model to identify terrorists trying to board flights with greater than 99% accuracy? It's possible. If you use the metric of accuracy for your model, it's quite possible that you could say, hey, you know, Homeland Security, by my model, I get 99% accuracy. It sounds good, right? If you say that, those words for a person that it's not in data science, you know, would say, oh, wow, that's a pretty good. But actually, as it turns out, if you look at this model and really understand the data behind this assertion, this is, you know, garbage, right? So this is, you know, tells you absolutely nothing. And actually, it's not, you know, it's not a good model at all. So, well, here's the model. Now let's understand the details of this, right? So simply, you know, to get that, simply label every single person flying from a US airport as not a terrorist. You would be almost correct, right? If you did that. You know, that's a model, you know, just, you don't have to build a machine learning algorithm. You don't even have to flip a coin. Press a button, person walks in, not a terrorist. Done, right? So you simply label every single person flying from a US airport as not a terrorist. The majority of the time, 99% of the time, you will be right. You will be right. All right, because think about the real, now think about the data itself. About 800 million average passengers, at least before, you know, COVID, right? Given there were 800 million average passengers on US flights per year. 800 million. That's a really, really large number. Wow. And since from 2000 to 2017, there were only about 19 confirmed terrorists who boarded US flights. Think about the difference there. So when you say that your model has a 99% accuracy, you'd be right? Because the majority of that, just 800 million minus 19, are not. And so that value, using the metric of accuracy, does not at all say anything about your model. This model achieves an astounding 99.99 whatever accuracy. It might sound impressive, but I believe if somebody, you know, people at Homeland Security will probably not choose your model, given that statistic, right? Because they'll say, you know, this person didn't even report precision and recall. How can I trust their model? It has nearly perfect accuracy. But this is a problem in which accuracy is clearly not an adequate metric, unfortunately. Okay, and so that's why you have to dig deeper into what you're trying to do. And this takes us to the idea, you can see it over here, of imbalanced data sets. Believe it or not, that will be the vein of your existence. You will never find balanced data sets, unfortunately. They will always, for the most part, be imbalanced. And what that means is, and highly imbalanced, like the one, you know, this scenario, for instance, you have terrorists, not terrorists. It's highly imbalanced because, oops, there's only 19 samples. real samples in the population. So imagine in the population, you will never have the population, you will have a sample. But there's plenty of examples to calculate features of not terrorists, right? Because there's 800 million of those, but there's only 19 actual in the population. And so you would really only get 3 or 4 at most, right? And so this is an example of what is called an imbalanced data set. A balanced data set, on the other hand, would be a data set like we saw with Iris. Iris had 3 classes, 1, 2, and 3, and each one had 50. Now, do you have to have perfect balance? No, not necessarily. But you want to have some balance. So for instance, I would say, and this is just my personal opinion, if you have like 20, and then this one is maybe 70, and then this one is around 40, I would still say it's somewhat balanced. There's still strong enough case for it to be balanced. If this one is 3, then okay, yeah, there's an imbalance there, okay? Certainly this is highly imbalanced, highly imbalanced. So the terrorist detection task is an imbalanced classification problem. We have 2 classes we need to identify, terrorist and not terrorist, with one category representing the overwhelming majority of the data points. So here, intuitively at least, you need a model that looks at the precision and recall and all those values on a per class basis. But also you want to have a metric that's overall. And again, as you saw in Weka, and this is why Weka is such a powerful introduction to the pipeline, is that you saw that Weka gives you that little table at the end, not only showing the performance metrics overall, but also on a per class basis. Okay? Does that make sense, guys? Are there any questions so far? No? All right. So another imbalanced classification problem occurs in disease, right? Disease detection, when the rate of the disease in the public is very low, right? So cancer, right? Something like that. In both these cases, the positive class, which is either disease, cancer, or terrorist, is greatly outnumbered by the negative class, not terrorist, not disease, okay? So that's an important notion. These types of problems are examples of the fairly common case, and you can see that, fairly common case. If you go into this field of applied science, whether you apply it to cybersecurity or self-driving cars or natural language processing, you will see that it's a fairly common case. A lot of you are scholars in cybersecurity, and I guarantee you a few years from now, when you're doing this kind of work, you'll be using these tools. Think of fraud detection, right? In a bank, Amazon purchases, etc. Most of the transactions are not fraud. Most of them are just regular transactions, but there are in there, cases of fraud. A small percentage, probably less than 2%, and so it's the same idea. Okay. Antivirus or intrusion detection in the network. Most of what happens in the network, the packets are just regular packets, regular traffic, and then every now and then, boom, you get an attack, right? So again, highly imbalanced if your goal is to find malware versus not malware, or intrusion versus not intrusion, and so on. So this applies to many, many, many problems. Okay, in the real world, it's kind of like that. We're almost always looking for the exception. And that's kind of the goal. So these types of problems, so in 5 minutes, we're going to take our 10-minute break, and then we will come back. We will start with Mitch just so that we can get, I want everyone to have access to Scholar, and then we will finish up these slides. So that should be the plan for today. All right, so just remind me when we hit 3:20. Okay, so these types of problems are examples of the fairly common case in data science when accuracy is not a good measure for assessing model performance. Okay. So now let's look at the other ones. So intuitively, we know that finding all negative data points in the terrorist detection problem is not helpful. Found all the not terrorists, that doesn't help you. And instead, we should focus on identifying the positive cases, even though they're very few, those 19, right? So the metric, our intuition, now that you know the definitions of the metrics, the metric our intuition tells us we should maximize is known in statistics as the recall, right? Which, I just defined. So the recall is the ability of a model to find all the relevant cases within the data set. And that's what we want. So notice here, pay attention, in this table, I have flipped the predicted and the actual, okay? And that's just, it's another way of looking at this. So just focus on this one now. I've also changed the terminology now to the common statistics terminology that you've seen before. True positive, true negative, false positive, false negative, right? So this will be the lingo that you often see people using. Okay, so we're going to use this for our example here. And in particular, but it's the same idea. So you can see the equation is down here, kind of written out in words. So recall, the precise definition of recall is the number of true positives, right? True positives being these, divided by the number of true positives plus the number of false negatives. Okay? True positives, false negative. Oh, sorry. False negatives. What you see is, that basically, just like we were doing before, right? The actual. Okay, the actual data. So true positives are data points classified as positive by the model that actually are positive, meaning they are correct. And false negatives, this one, are the data points the model identifies as negative that actually are positive. So basically, the ones that you missed, right? The ones that you missed. In the terrorist case, true positives are correctly identified terrorists, and false negatives would be individuals the model labels as not terrorists that actually were terrorists. And that's a bad thing, right? Because you missed them, okay? And the other case is with cancer, right? You said that tissue was not cancer, it actually was cancer. That's a bad thing because you missed it. You could have caught it early and prevented either an airplane accident or, further health-related problems. So recall can be thought of as a model's ability to find all data points of interest in a data set. Okay? Sometimes just looking at the equation is a little bit better. So the true positives, false negatives, and the true positives. So a very intuitive way of understanding recall is that you have terrorists correctly identified and terrorists incorrectly labeled as non-terrorists. And then these are the terrorists that are correctly identified, okay? So that's your recall there. All right. So it is 3:19. So let's stop here. Okay, let's take our 10-minute break and we will come back at 3:30. We'll do the West Lafayette Scholar, then we will pick up here. So just right here. And then we'll finish up these slides, okay? If you have any questions during the 10-minute break, just take a look at them. Mitch, so you think you'll be ready at 3:30?
Yeah, I will be.
Okay, great. So what I will do is what I always do. I'm going to exit out, create a video for this, and then I'll be back in 10 minutes. Okay, guys? All right. See you in 10 minutes.